Why an American socket might cause a fire in Europe. Picture this. You walk into a new apartment, flip the light switch, and instead of the familiar click in the warm glow of illumination, there's a loud bang, a flash of bright blue flame, the sharp scent of scorched insulation fills the air, and cracks race across the wall like jagged bolts of lightning, twisting in a dance of destruction. All this unfolds in fractions of a second, yet behind that fleeting moment lies an entire history, a story of wires you've never seen, though they surround you on all sides, inside walls, beneath floors, above ceilings, in every socket and switch. This is the invisible nervous system of our everyday life, the arteries and veins through which the energy of civilization flows, and if even the tiniest, almost imperceptible error slips into this system, the consequences can be catastrophic. Today, we embark on a fascinating journey through walls, across continents, across decades of engineering thought, to uncover one of the most underestimated yet vital topics of the modern world: electrical wiring standards in residential buildings, and how they differ across three key global regions: the United States, the European Union, and the Russian Federation. You'll learn why an American installing a European socket in his Texas home could end up in the hospital with third-degree burns. You'll understand why a European electrician encountering Russia's three-wire system for the first time in an older building might stand frozen in confusion, as if before an ancient chess puzzle. You'll discover how the simple desire to turn on a light bulb gave rise to entire empires of regulations, commissions, and standardization bodies, and how a difference in wire insulation color, conductor thickness, or plug pin shape can mean the difference between comfort and disaster. We'll peer into archives of engineering solutions, examine how wars, economic crises, technological breakthroughs, and even cultural preferences shaped the wiring now hidden behind your wallpaper, and why you simply can't copy another country's standard as easily as you'd copy a cake recipe. This isn't just a dry set of wiring instructions, it's a story of human safety, intellectual struggle, compromise, and brilliant solutions woven right into the fabric of our homes. And by the time you finish reading this article, you'll never look at a socket the same way again, because behind every volt, every ampere, every wire strand lies not just copper or aluminum, but centuries of accumulated knowledge, tragedies, and insights that keep our world running. It all began not with wires, but with fire, with that very moment when humanity first sensed it could master an elemental force. Electricity arrived later, but once it entered homes, it needed space, just like air, water, or light. The earliest attempts at electrical wiring in the late 19th century resembled scientific experiments more than engineering solutions. Wires were simply draped along walls like ropes, wrapped in paper or cloth, and sockets as we know them didn't exist. Appliances were connected directly to bare wires via screw terminals, so it's no surprise that fires were frequent guests in the homes of early adopters of electric light. In the United States, the first step towards systematization came with the National Electrical Code, or NEC, first published in 1896 by the American Institute of Electrical Engineers. And since then, this document has been revised every 3 years, evolving into a massive compendium of rules now spanning over 1,000 pages, where every detail is thought through to the millimeter, and every figure stems from the analysis of dozens of accidents, fires, and human errors. In Europe, the path was different. There was no single unified code, but a strong drive toward harmonization, especially after World War II, when devastated cities demanded reconstruction, and engineers realized that without common standards, safety across a continent where borders were becoming increasingly symbolic and goods increasingly cross-border was impossible. Thus emerged the IEC 60364 standard, an international benchmark for low-voltage electrical distribution systems, which became the foundation for national regulations in Germany, VDE, France, NF C15100, the UK, BS 7671, and many of these norms later formed the basis of the European HD 60364 standard, the so-called Harmonized Directive, which made it possible for a socket installed in Warsaw to be electrically compatible with a plug purchased in Amsterdam. In Russia, the path followed a different logic. During the Soviet era, a unified electrical supply system was developed for the entire country and later for the whole Union, and the key regulatory document became the Rules for Electrical Installations, or PUE, first approved in 1931, though its roots stretch back to Imperial Russia, where the first power plants were built following German and British designs. Yet after 1991, Russia found itself in a position where it needed not only to update outdated norms, but also integrate them into the global community, leading to the emergence of standards such as GOST R50571, GOST R5044, and many others. Standards that on one hand preserved the Soviet legacy, while on the other attempted to align with European approaches, yet still retained their own specificity dictated by climate, vast territorial scale, and construction history. It's crucial to understand that standards are not bureaucratic red tape. They are living documents born from blood and ash. After the 1903 fire at Chicago's Iroquois Theater, which claimed over 600 lives, the NEC introduced strict requirements for emergency lighting and disconnect devices. After the 1987 King's Cross Station disaster in London, where a fire in an escalator shaft killed 31 people, British regulations mandated extremely stringent rules on cable flammability in public spaces. In Russia, after a wave of apartment fires caused by overloaded aluminum wiring, the 6th edition of the PUE categorically banned aluminum use in new residential buildings, a decision that saved thousands of lives. Standards are not just paper, they are memorials written not in names but in numbers, cross-sections, colors, and diagrams. Let's now peer deeper into the very anatomy of wiring, into what lies hidden behind the wall where the most fundamental continental differences begin. The first thing even a non-professional notices is the voltage and frequency of alternating current. And here we see a clear global divide. 120 volts at 60 Hz in North America versus 230 volts at 50 Hz in Europe and Russia. In this difference is no coincidence. It stems from historical choices made early in the 20th century. In the US, Thomas Edison initially championed direct current but lost the war of currents to Nikola Tesla and George Westinghouse, who advocated alternating current. And the earliest grids were built around 110 volts, deemed the optimal compromise between safety and transmission efficiency. And over time, this rose to 120 volts. In Europe, where Germany and the UK pursued their own paths, engineers quickly realized that with the same line losses, they could transmit 4 times the power by doubling the voltage, since power scales with the square of voltage, and 220, later 230 volts became the standard. And after World War II, as European nations moved to unify their networks, this parameter was cemented as the pan-European norm. In the Soviet Union, 127 volts was initially used, tied to 3-phase networks with 127-volt phase voltage and 220-volt line voltage. But in the 1960s, the system shifted to 220 volts, and in the early 2000s to 230 volts to align with European standards. Though in practice, socket voltages in Russia today still often range from 215 to 240 volts, which is permissible under GOST. But voltage is only the tip of the iceberg. Far more important is how that voltage reaches the socket. In the US, the so-called split-phase system is used. From the pole-mounted transformer comes a single cable carrying 2 phases and a neutral, with 120 volts between each phase and neutral and 240 volts between the phases, enabling high-powered appliances like electric stoves and dryers to run on dedicated 240-volt circuits, while outlets and lighting operated 120 volts. In Europe and Russia, a 3-phase system is employed. 4 wires, 3 phases and a neutral, enter a multi-unit building, and typically 1 phase, neutral, and ground are routed to each apartment, delivering the familiar 230 volts between phase and neutral. This architectural difference directly affects conductor sizing. For the same appliance power, current in a US circuit will be roughly double that in a European one, meaning thicker wires are needed in the US to deliver equivalent power. Hence the standard 12 AWG, American wire gauge, size for US outlet circuits, equivalent to about 3.3 mm squared, versus the common 2.5 mm squared used in Europe and Russia for the same purpose. But here's another nuance. In the US, aluminum wiring is permitted in certain circuits, especially in older homes, though after a wave of fires in the 1960s and 70s caused by oxidized aluminum connections, installation requirements became extremely strict, and today copper is used almost exclusively in new construction. Whereas in Russia, aluminum has been banned in residential wiring since 1997 under the PUE, and in Europe its use is highly restricted, though in Germany, for instance, aluminum can still be found in backbone lines of 1970s apartment buildings, just not in outlet circuits. Another critical aspect is insulation. In the US, the standard residential cable is NMB, non-metallic sheathed cable type B, composed of individually insulated conductors inside a shared plastic sheath, and this cable is run exposed inside walls, without conduit, because the outer sheath itself is rated for direct contact with wooden framing. Whereas in Europe and Russia, cable is typically installed inside protective conduit, PVC flexible tubing or metal sheathing, especially in load-bearing or concealed walls, due to requirements for future cable replacement without wall demolition and for fire safety, as conduit-contained cable won't propagate flame throughout a wall cavity in case of ignition. Wire color coding is perhaps the most visually striking example of continental differences, and simultaneously the most dangerous for the uninitiated, because confusing live and neutral is like mistaking the gas pedal for the brake. In the US, per NEC, the live, hot wire must be black or red, neutral, white or gray, and ground, green or bare copper, and this rule is so strict that even in three-phase systems, only black, red, and blue are used for phases to avoid confusion. In Europe, since 2006, a unified harmonized color scheme per EIC 60446 applies: brown for live, blue for neutral, and green-yellow for ground, and this governs all new installations, though older buildings may still feature legacy coding, black for live, gray for neutral, which confuses visiting electricians. In Russia, until 2013, the national scheme used white, red, or black for live, light blue or blue for neutral, and green-yellow for ground. But after GOST 31996-2012 came into force, fully adopting the European standard, Russian practice also shifted to brown, blue, green, yellow. Though in older buildings, white insulated wires persist, and many electricians still habitually use black for live, creating real hazards during renovations. Imagine this scenario. A US electrician arrives in London for a job, picks up a voltage tester, and sees brown as live and blue as neutral. Familiar. But if he accidentally encounters an old black and gray cable, he may assume black is live and gray is ground, whereas in reality, gray is neutral. So disconnecting neutral instead of live leaves voltage on the appliance chassis, leading to electric shock. Even more perilous is grounding. In the US, the ground wire is often bare, as it shouldn't carry current under normal conditions and is simply attached to metal box parts, whereas in Europe and Russia, grounding is always insulated with a green-yellow sheathing to prevent accidental short circuits during installation. And here arises the question, why such divergence? The answer lies in safety philosophy. In the US, emphasis is placed on circuit breakers and ground fault circuit interrupters, GFCIs, which trip at leakage currents as low as 5 milliamperes. So even if someone touches a bare ground wire, it won't cause a fault. Whereas in Europe and Russia, priority is given to physical protection, insulation, conduit, sealed junction boxes to eliminate contact possibility altogether. This isn't about which is better, it's about philosophy. Americans trust electronics, Europeans and Russians trust mechanics, and both approaches work, but only if you follow your system's rules, not mix them. Sockets and plugs, the part of electricity we interact with daily, seem so simple until you wonder why pin shapes vary so dramatically from country to country. In the US, the NEMA 515 standard prevails. The outlet has 2 angled flat pins and 1 round grounding pin, and the plug inserts in only one orientation to prevent live neutral reversal, though for most appliances polarity isn't critical. For some, like incandescent lamps with screw bases, it matters that live reaches the center contact, not the threaded sleeve, to reduce shock risk during bulb replacement. In Europe, the dominant CEE7 standard, the so-called Europlug Type F, features 2 round pins and 2 side grounding clips, allowing plug insertion in any orientation, no polarity, but ensuring robust contact and high-touch protection. Fingers can't reach live parts even with partial insertion. In Russia, GHOST 7396 specifies full compatibility with European Type F, yet with one key distinction. Russian sockets must include an integrated switch to de-energize devices without unplugging, a requirement born from Soviet-era practice when homes lacked individual circuit breakers, and the only way to turn off a TV or fridge was via the socket itself. But the most intriguing feature lies in protection ratings. In the US, sockets in bathrooms, kitchens, garages, and outdoors must be GFCI protected, tripping at a 5 mA imbalance between live and neutral, nearly instantaneously cutting power upon human contact. Whereas in Europe and Russia, such locations use splash-proof sockets with covers, and protection comes from group-level RCDs, residual current devices, set to 30 mA, slightly slower but reducing nuisance trips from surge interference. Cultural differences abound. In Japan, where voltage matches the US but frequency shifts from 50 to 60 Hz across the Fuji Mountains, sockets resemble American ones but lack grounding, causing issues for tourists with grounded plugs. In the UK, the unique Type G socket, 3 rectangular pins with a 13-amp fuse built into each plug, persists, a legacy from when wiring was weak and each appliance had to protect itself. In Australia and New Zealand, sockets look American but with pins angled at 120 degrees, deliberately incompatible with other standards. This diversity isn't whimsy, it's the result of centuries of adaptation to local conditions, material quality, public electrical literacy, earthquake frequency, humidity levels, copper and plastic costs. Every socket is a compromise between safety, convenience, cost, and the technology of its era. Now let's discuss the most vital element, protection, because wiring alone is just a piece of metal. It's the protection system that transforms it into safe infrastructure. In the US, the focus rests on ground fault circuit interrupters, GFCIs, mandatory wherever water contact risk exists. And these devices are so sensitive they trip at 5 mA within 25 milliseconds, faster than human pain response, saving lives. Per the National Safety Council, household electrocution deaths dropped over 70% after mandatory GFCI adoption. In Europe and Russia, the analogous RCD, residual current device, is typically installed per circuit group rather than per outlet, with a 30 mA trip threshold, considered sufficient to prevent ventricular fibrillation, though slower to react to light contact, yet reducing false trips from aging appliances with high inrush currents. Beyond RCDs, Europe and Russia widely use RCBOs, combination devices integrating RCD and circuit breaker functions, tripping on both overload and leakage, whereas the US typically installs separate breakers and GFCIs, as NEC requires each GFCI to have a test button for monthly user verification. Another key difference lies in circuit breaker philosophy. The US uses thermomagnetic breakers, tripping via bimetallic strip heating under overload and electromagnet action during short circuits, with ratings precisely matched to cable size: 20 amps for 12 AWG, 15 amps for 14 AWG, and exceeding even by 5 amps is prohibited as it risks insulation overheating. Europe and Russia also use thermomagnetic breakers, but employ modular DIN rail systems, with ratings adjusted for demand factors, accounting for not all devices operating simultaneously, and for a 2.5 mm squared outlet circuit, a 16-amp breaker is typical, though 20 amps might be calculable, with margin added for insulation aging. Crucially, in the US, installing a breaker exceeding cable rating is forbidden, even with light loads, because inspectors verify NEC table compliance during final inspection, and non-compliance halts occupancy approval. Whereas in Russia and parts of Europe, for reliability, 25-amp breakers on 1.5 mm squared cables still occur, gross violations and direct fire hazards. US oversight is stricter. mandatory pre-occupancy inspection and licensed electrician certification, whereas in Russia and many EU nations, checks often obey formalities, creating a safety gap at the household level. Yet Europe imposes tougher fire safety cable rules. CPR, Construction Products Regulation, fire reaction class is mandatory, with class B2CA or higher required for dwellings. Cables must resist flame spread and emit minimal smoke or toxins, while in the US, such rules mainly apply to public buildings. Private homes may use standard PVC insulated cable, which emits toxic hydrogen chloride when burning. This doesn't mean one system is superior, it means each adapts to its context. The US trusts active protection, electronics. Europe trusts passive protection, materials and construction. If you think these differences end with wires and sockets, think again. They extend even into distribution panels, the metal boxes in your hallway determining whether your home has light or darkness. In the US, the breaker panel is a metal cabinet with rows of circuit breakers mounted on 2 bus bars, each breaker connected to one or both phases for high-power devices, using odd-even numbering to balance phase loading. In Europe and Russia, panels mount DIN rail breakers in a single line, with phases distributed via comb bus bars for easy reconfiguration, and always include a main breaker, RCDs or RCBOs per circuit, and separate neutral and grounding bars, where PUE and European norms require neutral and ground separation after the main device to prevent ground current flow and false RCD trips. In the US, neutral and ground bond only at the main panel, strictly separate elsewhere, or leakage current could bypass via neighboring ground wires, causing GFCI failure. Another distinction, accessibility rules. In the US, panels must remain unobstructed with 75 cm width and 90 cm depth of clear working space, whereas in Russian Khrushchev-era apartments, panels are often tucked behind built-in cabinet doors, barely reachable even in daylight. Here lies the core question. What if you live where standards differ from those you know? Say you move from Germany to New York with a European plug coffee machine. Can you just buy an adapter and plug it in? Technically yes, but practically risky. The machine expects 230 volts, but the outlet supplies 120, so it may not start or run at half power, yielding lukewarm, tasteless coffee. A step-up transformer helps, but remember, current doubles. So if the circuit is 15 amp protected and the machine draws 1.5 kilowatts, at 230 volts that's 6.5 amps, but at 120 volts it's 12.5 amps, nearly the limit, and adding other devices may trip the breaker. Conversely, plugging a US device into a European outlet is riskier. A 1200-watt hairdryer draws 10 amps at 120 volts, but only 5.2 amps at 230 volts if connected without a step-down transformer. Doubled voltage burns out the coil in seconds, or worse, ignites it. Thus, globalization demands not just linguistic but electrical fluency, and increasingly manufacturers produce appliances with universal power supplies 90 to 260 volts, 50 to 60 hertz, usable from Reykjavik to Vladivostok, but always check the label. Input 100 to 240 volts, 50 to 60 hertz is safe. 120 volts, 60 hertz only means don't risk it. We've reached the end of our journey through the invisible arteries of our homes, and one simple, fundamental truth stands out. Electricity isn't about volts and amperes, it's about respect for life, for the labor of those who designed, built, tested, aired, and learned from mistakes so that today we can flip a switch and see light without thinking how that gesture embodies a universe of norms, calculations, compromises, and decisions forged not in bureaucrats' offices, but in labs, on construction sites, in fire stations, and courtrooms. Differences between US, European, and Russian standards aren't barriers. They're mirrors reflecting distinct technological paths, priorities, climates, and cultures, but all share one goal: human safety. So next time you replace a socket, remember, behind every wire in your wall lies a story. Behind every insulation color, someone's life. Behind every breaker in the panel, someone's pain and insight. Don't hesitate to ask questions. Double-check your electrician if something seems off. Verify cable markings. Study PUE or NEC. Watch tutorials. Attend courses. Knowledge here doesn't just make you smarter, it makes you and your loved ones safer. In a world of ever more complex technology and dwindling trust in professionals, personal literacy isn't a luxury, it's a duty for anyone who wants their home not just cozy, but secure. So let's make the world a little brighter, not only with bulbs, but with awareness, attention, and respect for that invisible yet vital engineering flowing through our walls like blood through civilization's veins. And remember, as long as electricity flows, hope remains, but only if we recall that behind every volt stands a person who chose how to use it right.